Well, good morning, everyone. Very interesting session before me from Naira. Learned a lot. Uh, I'm Ajay Sharda from Kansas State University. I'm in the Bio and Ag Engineering department there. My partner in crime, Dion, could not come in for some family reasons. We are a small group at Kansas State. We're working on different color infrared and the thermal infrared camera utilization in ag. So I'm going to talk something about what he asked me to present on his behalf, and then I'm going to share some of our experience on with thermal infrared cameras. Well, to quickly start from like what has happened in the recent past is just about this talk is everywhere. We are looking at talks on data from every part of the country. So data revolution in terms of having this huge amount of information which is available to make all these field level decisions, that has driven a lot of things. Whether it is precision ag in terms of variable rate technology, understanding yields, understanding the variability in soil, and understanding all those things which are happening in our field. That's one of the most important thing which has come in the picture. Now, the thing which has been going around is the data part is there, and there are startup companies, there are faculties, and everybody's kind of scrambling around is what to make out of that data, how to transform that digital piece of information into a knowledge-based decision-making aspect of it. A lot of what I will say on my, that is my personal opinion, is a lot of service providers who are big equipment dealers and who are also big service providers to their local farmers or users. They are by far on top of the curve in terms of understanding which data layers matter the most in terms of making a decision for a certain thing. Say, for example, if I want to make a decision for variable rate seeding versus variable rate irrigation, which data layers should I play with? Because there are so many data layers out there, and you can easily get bogged down by, should I look at 5 data layers or 3 or 4 or whatever. So which are the best data layers to play with? That is the most important things. Now, what has happened in the recent past is the onset of unmanned aerial vehicles. Now, what has been going on in ag communities, you go out, you scout the field, you look at certain areas in the field, you look for certain specific knowledge-based information, then you kind of extrapolate our whole field, and then you make some assessment in terms of, okay, this is what I want to do, and you make some decision. But with UAVs coming in and the flexibility of these systems in terms of capability to fly whenever, ideally saying whenever means I can fly much more than making 1 or 2 trips in my field, and I can fly over the whole field in terms of getting that information is what is driving a lot of aspects. Cost, sensors are out there, which their cost has come down, and the data management, we'll talk about that. Quick image of what is going on, what was going on at K-State in terms of research. There are people who are using handheld crop sensors to go out and collect some data. As you all know, or most of you know, that when I'm using something like a green seeker, I'm getting a point data in terms of whatever is in the field of view, and that is one data point. And then I keep walking all along the field, all along the row to get some piece of information. So what a UAV can do is, I can put my sensors in a UAV and I can fly much quickly to get the same kind of information. Initially, when I was not there at that time, and Dion and Kevin and other people were getting into this business. They want to make sure that how do these cameras, they pan out vis-a-vis crop sensors like green seeker and all those things when you go out and collect a similar piece of information. And what you're looking at is 2 different maps, and then one in terms of the data we have collected, and the curves on the right, which actually is a comparison between the images taken from a camera on a UAV versus a green seeker, the correlation between them is amazing. For a biological system, a correlation of, the R-square value of something in the range of 0.9 is kind of a more than ideal, kind of throw you in a picture that is it real, or, you are tweaking a data or that. On the left, red NDVI composite aerial map, what you're seeing is those white lines are, the data point which a graduate student was holding a green seeker and he was going point by point by point, collecting that data, versus the whole map of this aspect. Another aspect which I want to stress in this image is identifying some of the subtle differences which exist in the field. Like in the color image, which the purple thing we were seeing is all the sandy portion in the sand where the leaching is going on in terms of nutrient and water. So those differences are much easier to see with the cameras on the UAV versus when you go out and scout those things, from point to point. Now I talked about the platforms in much more detail. I'm not going to go in that, but what we have on our disposal is both the multi-rotor and the fixed wing aircrafts. When we go out to talk to people in terms of people in the camera business, people in the service providing business, people who are getting into an aspect of providing these kind of services, the first thing which comes into their, in the discussion is the productivity kind of a thing. How quickly I can go out and collect those images. The next question is how much time is it going to take to process all those images. All right. The next question is, so how quickly I can get that information back to my machine to do some variable rate aspect of it. So all these questions, they are important, and we're trying to answer some of them all along. But very obvious, both the platforms, they have their own disadvantages and advantages in terms of what they do. If you talk to anybody, if you talk to 100 farmers, probably 90 of them are going to say that I'm for the fixed wing aircraft, just unknowingly, because they think like this is going to be the faster, the most productive, platform to do it. From people like us in the research area, I think the multi-rotor are going to play a much important critical role for us, just from the purpose of vertical takeoff and landing aspect, and going out and working or testing our systems or imaging systems or whatever you're working on a quick span. I want to go out, collect some data, come back and look at how does it look like. It's much easier for a multi-rotor versus a fixed wing. Before I get into some of the things what I want to share today, one, two or three things which are the most important driving factors are some of the resolutions which are associated with that. The first thing I'm going to talk about the spatial resolution aspect of it, because there are things, there are manned missions, there are satellite things which are going on, and there are new satellites being launched for both thermal and other spectral bands. But what you see is going from the the bottom right corner and all the way to the top left corner in terms of what can be differentiated in terms of when you go from a lower spatial resolution versus a very high spatial resolution. From a lower spatial resolution, you can just make some subtle trends you can put out, but when you are on a higher spatial resolution, that is what you can do. The image on the right is taken with a color infrared camera on a multi-rotor, and what we are seeing is a 3 millimeter pixel size resolution on a plan, which is much higher than anybody will lead. But some of the phenotyping work people are doing, probably that becomes more of a thing. Another aspect of that is the temporal resolution aspect of it. That I get some information at the beginning of the growing season, and then I get some information towards the end of the growing season. But what happens during the growing season is going to play a much important critical role in ag in coming years. I really want to make sure that if there are some things which are happening in my field, then I should better be able to make those decisions during the season rather than towards the end of the season when everything is all said and done. This is looking at red cedar trees in the background of other trees, for different time frames. Similar things are applicable for phenological studies. This is catching up very fast. Um, it's not in U.S. people in. I was talking to somebody from Chile and Brazil and Africa and people everywhere. They want to figure out what the different genotypes and phenotypes they do in terms of stress and all that. The other aspect of that is the radiometric resolution. We can use these systems and we can differentiate much more intensities vis-a-vis what we can see from a human eye perspective. For example, an 8-bit can differentiate in anywhere from 0 to 255 different, so 256 different pixel intensities. Human eye can do only 16. So if you go from 8-bit to 10-bit, or maybe some of the digital systems are doing 14-bit, and you take out all the noise, you're still within the range of 10, 11 bits. It's much, much more and much accurate information to play with. There are the people working with systems which are manned missions and satellites, and I think both these systems are gonna be around and gonna be complementary to each other. But some of the advantages which the low altitude flying gives us is all the effects of atmospheric degradation of your data which is going on. That is much lesser than what will happen with the manned missions. In terms of accuracy to fly over and over again in a very accurate and repeatable manner, which Naira just pointed out in her presentation, there is an advantage. We can set up some of the missions, and I can come 10 times, during my growing season. I can fly over and over again. I can see what is going on, with my thing. Quick comparison of what a picture from a satellite versus high resolution SUAS might look like is the one on the left is coming from a Spot satellite, and the one on the right is from a UAS. Same field, pretty much around the same time, and what you can see is that the image from a satellite is giving you very kind of a broader trends between your fields, low versus high NDVI values in terms of what might be the differences, out there. But if we see some of the high resolution images, we can point out some of the areas, where those dark lines where the planting was not done well, where there are some planter errors were going on, and so on and so forth. We can start to narrow down what were the reasons for, or we can go back and see what is the ground thing. Somebody was asking me earlier this morning that we still have to go out and scout. That is definitely has to happen, because we have to go out and see, if I see some differences, whether there was a plant or not, or the plant is diseased, or plant is nutrient deficient, or water, or what is going on. This is another image by Dion. What you see, I want to point out the temporal aspect of it. The image on the left and the image on the right, it's a cone thing, and what you're looking at in terms of the red portions, which are the low NDVI values, are the areas of the field which are affected by spider mites. All right, so if I can fly in and see what is happening and just in a period of another 10 to 12 days, just see the effect of spider mite, which has kind of exploded in the whole field. So the aspect of temporal thing, if I can go in, if I see this kind of a deal going on, I can take some remedial action during my planting season. I can do something. Otherwise, 10 days later, I can see something more. Yeah, please.
So I noticed on the last NDVI scale, red was high, which I've seen in a bunch of places. Is it just arbitrary which colors you guys are picking, or is there a reason for using green high?
Green higher, yeah. Well, green, just by human nature, green higher means, something like a healthier, and red doesn't. Another aspect of, what is going on is, in terms of this high resolution aspect of, what we are talking is the classification and damage quantification. On the image you saw in the last plot, we can just come down, we can classify what bands of NDVI represents the damaged area, what parts represents no plants at all, like complete dead crop, and some portions where the crop was healthy, and we can start to make out, some sort of a quantification in terms of how much area is healthier at this time, how much area was damaged, and all those things. So this is sure,
I
please.
have a question.
Sure.
Sorry.
No, please carry on.
Have you found that those bands are fairly consistent for NDVI imagery, or is it just based on per field, per crop for that year, we baseline it for this?
Well, some sort of a field-to-field thing has to be done to be accurate. They can be consistent for a region or for a platform, what you're doing in that region. But from my standpoint, I will still go in to make sure I cross-check where I am in terms of those bands before I start to make, especially these classification, and any kind of a analysis for site-specific or variable rate application things or decision making. We're gonna switch gears here. I'm gonna talk something about. So this was quick recap on some of the things we are doing on color infrared cameras. Another aspect we are carrying on is the thermal infrared aspect of it. Some of the motivation came from the aspect of the irrigation water, how scarce they are, how limiting they are in terms of where they are, in the Great Plains area of Kansas, Nebraska, and South Dakota, and all the adjoining regions. Water supplies are going down. People are finding advantage of irrigation, and they really want to capture the best possible benefit from whatever level of irrigation water is available to them. There are current approaches which are again either point-based, whether you use soil moisture probes and all those things, or infrared thermometers, which people have been using to assess the crop canopy and then relating that canopy temperature back to the soil moisture content. But all these things are first of all point-based. They have, thermometers have limitations in terms of when they can be used. They are typically mounted on pivot systems, which can only go for certain times, cannot be operated at night. So there are lots of aspects of, what kind of a temporal resolution you can look at. So this was one of the motivating factors for us to go forward. Thermal infrared cameras. Some of the advantages from thermometers is in terms of the average. What the thermometer is doing is whatever is in the field of view of that thermometer, whether it is soil or canopy or a mix of soil or canopy, it's going to take an average and give you one value. But what the thermal infrared cameras can do is it will give you an average value within each pixel, and depending on how you fly and what resolution of a camera you have much more pixels within the same field of view in terms of differentiating what was what. High spatial resolution, that is ideal numbers, less than 10 mm, but it depends on how high you're flying, what is the field of view, the angle of the lens, and all those metrics of your camera system which comes into play. We brought these systems in. They're mostly uncooled cameras and not the cooled ones, and we did some strict lab kind of experiments to understand how accurate they are by mounting some thermistors in a very controlled environment, and we could very easily get an accuracy of what the pixel was telling vis-a-vis what our instrumentation was telling within plus or minus 0.4 degrees centigrade. That was pretty neat for us. And then obviously the potential of whole field mapping is another one. Some of the other advantages which I see is the whole aspect of getting the whole field, a spatial temperature map in an image. We can bring all these images and we can very easily do some image analysis in terms of pulling or segmenting the crop versus the background image, background soil aspect of it. These cameras are uncooled, they're low weight, they are much more cheaper than versus the cooled cameras, and then their ability to fly low altitude is what is pushing us to go forward. Spatial maps of crop water stress to link soil moisture. This is by far the biggest deal. If we can go out and fly and get a thermal map of the canopy and then give an aspect of, okay, this is what your soil moisture look like on a spatial basis, is will be the biggest deal coming out of this work. And obviously, informed decisions when we are talking about variable rate irrigation, the newer systems out there, but they're not able to do what they're doing. There are a lot of aspects of plant, environmental versus plant influences, which goes on when we are talking about how they transpire, what conditions, like ambient conditions, whether this is the air temperature, the relative humidity, all those things, they play out to do some of those things. So this was going forward, but some of the limitations what we saw moving forward was these systems have been used more so in an industrial setting where the resolution or the accuracy is not much of an issue. And there is very limited knowledge which is out there in terms of what camera configuration should I go for, what kind of a camera settings in terms of internal intrinsic properties, their effect on the performance, on the accuracy of the camera behavior. Those are pretty important for us to understand before we go out and use them. Specifically, their accuracies in dynamic field conditions, because it's not a air conditioned aspect, or it's not a structure. When you're out in the field, there are not extreme, but there are wide variations in terms of ambient air temperatures versus humidity and the wind speed and how it's blowing in from where. So some of those effects, and in the aspect of people working, trying to improve their imaging systems, and people working trying to get in very good working platform to get that, but little work in terms of integrating or providing integrated solutions for agriculture. So I'm going to quickly show some of the things which we saw in terms of when we were going out to develop an automated system. What we did, we collected all the things we need to see how well these camera systems can capture the thermal imagery over a period of time, and then what other sensors and we need to derive things like crop water stress indexes, and then we wanted to correlate back to soil moisture content, that does it correlate to the moisture content or not. So we pulled together all these sensors, pretty typical. People know it in the solar radiation, data AC and air temperature, humidity, soil moisture, some things to put all the thermal thing together. We put all this. Sure, please. So what we did, we put that all in a greenhouse. We laid down two different treatments. One was an irrigated crop, and another was a water deficit crop. And the system can take images every 2.5 minutes. It's used to pull all other ambient condition aspects of temperature, relative humidity, and it all has a webcam as well to give us an idea on what is going on. And then we could monitor and play with our image processing and everything back in our lab. We don't have to go in the greenhouse again. Irrigation system was also automated, so we were very accurately controlling the amount of water we were giving, and we were also monitoring the moisture of the water stressed crop, and we really don't want to kill those plants. And if there was a point when they were, and we watered them for a little bit. Once those images were with us, we segmented out the canopy versus the soil background, and then start to play with what those pixel intensities look like. Now, one of the important things we have these in the bottom right corner. We made a small reference panel with nearly close emissivity of what we could figure out, and then we used very accurate thermistors. So those reference panels were there in every image. So every image has a pixel intensity versus actual temperature aspect of it, so that we can develop a calibration curve for every single image we have, and then we used to assign the quantitative temperature values to all those pixels.
What was the resolution of the thermal imagery?
So 0.4 is what we got in the lab, and I'll come back with another plot in terms of what we what we could get in a greenhouse environment over an 80-day growing period. So what was done? So all this setup was there in a greenhouse. We monitored, we captured thermal imagery, we captured the soil moisture, air temperature, relative humidity, for all the water stress versus the well water plant for 80-day period, and then everything was coming in, and we were trying to see what are some of the effects. We used some of the very typical thermal indices to derive the crop water stress. Some of the things are we need some of the coefficients from the well water crop to derive the crop water stress index, and I'll show you what we gathered from that. Now, from the 80-day period of the study, this is an average of what was actually measured versus what the pixel intensities were telling, and we were within plus or minus 6 degree accuracy in terms of what the pixel intensity and the temperature values were telling all along. Since we were capturing data day and night, we learned quite a bit in terms of what is happening during the transition times when from dawn to dusk, when the temperature differences between the air and the canopy are very subtle, and the noise levels which will come into play. This is a small screenshot of the data, what we got from between 12 noon and the evening, and the dark line, solid line is what we measure, and the dotted ones are the confidence levels or intervals we were between. Now we talk about calculating the crop water stress index, and we need some coefficients in that. What we did, since we were monitoring all these data during the 80-day period, we segregated that into crop stage 1, 2, 3, and 4, and then from there on we plotted the differences between the canopy temperature and the air temperature, which was actually we were measuring, and then we can also calculate the vapor pressure deficit, and we could come up with our own plot, and then it gave us the slope and the intercept needed for calculating the temperatures of the canopy for a well water, and some of those data points. Some of the interesting things we learned are on this plot. What you're seeing on the plot on the left is the day of the year, and the y-axis on the left is the crop water stress, which was derived using the canopy temperatures, and on the right is the soil moisture content. So we started up on day 0 when the dotted red line and the dotted blue line, which represents the well water, and the stressed is the red again. So you see we were maintaining the moisture for the well water all the way, and then also the crop water stress was in between 0.2, 0.3, which is normal when there is enough moisture in there. And when the moisture or soil moisture dropped for the water deficit thing, the crop water stress starts to increase, in a very nice trend. And then at some point close to the day 50, they were at close to wilting, and then when we watered them and back again. So overall, what we learned from a plot on the right that we could go out and collect thermal images, and based on those canopy temperatures, we can predict what the soil water moisture will be pretty much 82% of the time, which is pretty neat. This is so all the data we were collecting, we actually put together all the images into one big movie where you could see the plants growing, and this was all the data which was coming in every 2.5 minutes in terms of air and relative humidity and solar radiation, and then every image was given a scale in terms of what the temperature looks like. At some point you'll see, you're seeing the black and white regions in terms of on the right and left, which are well water versus the water stress things. So you also see some of these noises in the images which were during when the sun, during the sunrise and when the sun set, because of the relative differences, very subtle differences between the air temperature and the canopy thing. So this was this gave us a nice understanding of what was going on. It's pretty amazing to see, during the end of the season when they were really stressed out. We could see the leaves swirling and trying to save some water all along. Another piece to the whole thing was, can we put these images together and create a mosaic. We also created a small table in terms of how quickly you can put these images together, and it doesn't take much long. Somebody asked this question, so how long? 15 minutes, half an hour, 1 hour? So it's very difficult to give a very quantitative number to what time is going to take, but depends on how good the data you have, and how well you flew and everything, and that all depends on the stitching. Yes.
A couple of quick questions about this one.
Sure.
Did you deal with lens distortion at all?
So some of the cameras, like the FLIR ones, the lens angle is 67 degrees, or some are even more. The ones which we use from the company called DRS Technologies. Their lens angles vary anywhere from 11 degrees to 22 degrees. And we did a test in terms of understanding the lens distortion. It was much lesser than what we saw in the FLIR, in the wide angle. I'm no one to say it is this company or that, but obviously when there is a wide angle, you'll observe that lens distortion much more than the narrow angle, and there were.
What was the focal length you used for this? Just that case?
No, not on top of my head. Yeah.
And what altitude was this flown at?
So this was flown at 40 meters.
Oh, that's pretty low.
Yeah.
Okay. So
Yep.
narrow angle, very low.
Right.
That's why you noticed it.
Well, we also flew the same system on a golf course, which was at 100 meters, and it came out pretty well as well. You could see some ledges here and there, especially on the terrain side when there was a roll and everything, but it was still not bad. And then
But you still didn't get a lot of distortion.
No.
You were using a narrow lens.
yes. So this was all the analog system aspect of it, and we really think that if we can move from analog to digital aspect of it, we can do much better in terms of what we achieved. So that is all I've got. Any questions? I'm more than happy to answer.
So I asked about the resolution of the image. Was that a 640 by 480 resolution?
This was 640 by 480.
Have you experimented with anything bigger than that?
There is no, we don't have access to any of the cameras.
I haven't seen one either.
No. Earlier we started with 320, 280, and then we got to 640, and that is the maximum. We learned a lot in terms of camera aspects of it, the body heating up and its effect on the accuracy, the aspect of medium in between, the air temperature and the humidity, they play a role in terms of how they can affect what you're measuring from a height. But it is pretty predictable. You can narrow down, you can understand what is what. And the digital aspect is pretty good, but what these cameras they have is, we can set a gain and the level, like what range of temperatures I want to measure today, and everything else will be saturated. But when you go digital, you don't have that type of control. You will measure the whole range from minus whatever 40 to plus 100 something.
24 to 52.
Right.
Did you guys ground truth any of this to see how close it was?
It was less than 1 degree centigrade. So
The variance was always less than 1 degree?
Yeah.
Okay.
Yes.
Do you use any hyperspectral or LiDAR-based sensors?
We are not. We just started this thing last year. Now we are building our own imaging system, like whatever we need to pull all data points or all different types of data we need in one data stream. And we're hoping to go out and fly this year to see how accurately we can do, in a field environment. Sure. No, go ahead.
How big of an area is that?
This was 20 acres.
Okay.
Yes.
Just looking at the cam.
Mm-hmm.
Do you have any comment on how they rank or?
I have not used, frankly. Dion would have been a better guy to answer that question. But they are good. I was in Washington State University before coming to K-State. And there we have this 6-band camera from Tetracam thing. They were pretty good actually on what they were doing. They were working. They were looking at, the, I don't know, the apple's gas, some diseases going on. Can they predict, the apple is going to be sick or not? I don't know. And the quality of the harvest, and they were pretty happy with that. Yes.
Have you tried doing any manned versus unmanned to compare the results with your aviation?
No.
So you're not doing any of the manned, like
No.
just you?
Like something on a plane, no, we are not. So there are already few companies in Nebraska who are giving these kind of services. The idea is to kind of learn some of the dynamic aspects of these systems out in the field scenarios, both for the multi-rotor versus the fixed wing aspect. What we're looking at different altitudes and all the ambient thing aspect. Can we pull whatever we have learned in the lab and use that knowledge to do whatever corrections we want to do, and once we get there, then we will kind of compare, what is what. Yeah.
I have a quick question.
Sure.
You talked a little bit about the different resolutions, and I know that with UAVs, you get 1 to 5 centimeter resolution. Have you seen a real practical difference going up to 5, 6, 7 centimeters of resolution? Is there any real usable practical difference for precision ag applications between 7 and 1?
There is, especially looking at, post-planting thing, looking at emergence aspect of it, looking at some of the things like the disease aspect of it. You can actually come down to a plant level if you really want, or if you really want to look at the trends, what is going on, you can do at a much, lower resolution, or what to say. But the way we are going in ag, and the way we really want to do big whole implement section, we're down to a few sections and now each row kind of a thing. I think that will have some benefit. And we saw some images where we got the NDVI, and then there was one very difference between the same planter, everything going on, and certainly what that guy gave us was the error which was going on with the planter itself, like the oil leakage within that specific row did not let that row germinate really well than all other rows. And then somehow when it, all the oil was gone, which was like a couple of rows, and then you start to see the emergence back on. So looking at that, and also the aspect of my areas again, I really want, my thing is I'm pulling all this thing to integrate that with precision ag. So looking at some of the delays in terms of planter response on headlands, planter response on when things are changing in the field, how accurately, how quickly you can implement those changes. That is where this information will come very handy. And the whole aspect of wireless, the next thing is we really don't want the data to, the plane to come down and then do something. The aspect we really want to do something on the fly. Yes.
Just one question. So K-State, through their test site agreement, has recently been granted, I guess, permission to kind of expand the coverage like across Kansas, right? So do you have any insight into that? I guess that's good for you, right?
Well, K-State Salina, they have applied aviation school there where they test all the platforms. They have multiple, whether they are gas powered or battery powered, multi-rotor versus fixed. They train certified pilots for that. We get a lot of people who are getting internships or training, so we can have access to a lot of free, sort of very economical, I don't want to use the word cheap, but economical skill where we can hire those certified pilots to fly planes. What we got recently was a COA, which is a statewide Kansas COA to fly, and I was listening to the 333 exemption and everything, and that is it's very kind of a very subjective and sort of very objective in terms of what you can. So we got that for a certain platforms, but what that has given is now we can conduct research anywhere in Kansas. We can use that platform. We will have access to the certified pilots, and we can fly. We can adopt few farms. We can do accelerated studies. People are interested in phenotyping and the animal health aspect of it and the crop health aspect of it. Understanding the machinery behavior aspect of it. So, any more questions? Well, sure, go ahead.
Sorry, so you talked about thermal and you talked about reflectance.
Mhm.
Are you guys looking at any, either stream or static analytics between those two? So how does reflectance and thermal affect each other? And if so, are you guys publishing papers on any of that?
We just so when we get into the complexities of the image analysis part of it is where it will come. We need multiple data sources to get down to what we need, or you can have much advanced algorithms. Maybe I have to go to Naira at some point to see. So there are lots of things which are existing. We're working through, looking at pixel by pixel aspect of it. And depending on, so this is what we want to learn, how high altitude factor, lens angle and everything, because it's so easy to keep throwing all the data which has partial soil versus partial canopy. And then what you will left with is maybe just 20% of the data points, or maybe 50%, I don't know how much. And it will also depend on the growth stage of the crop as well. So we are working to develop a little more advanced algorithms where we can extract information from within the pixel itself, even if it has two different components side by side. So that'll be a key. That'll be definitely a key. All right. He's saying time is up, so grab me if you have more questions, and I'll be more than happy to answer. Thank you.